So this is first thing is about mass balance. As you know, we have to determine what's the total maximum daily load. That means we wanted to calculate amount of mass that's being delivered by a stormwater into those systems. So let, for example, we say this is our system. That system could be a pond, it could be a lake, or it could be a portion of a river, or it could be a green infrastructures. So we wanted to know how much pollutants are delivered into the systems by a stormwater. So that means there will be input that's coming in. So let's say this is storm water input. So that means there will be a flow rate. Then there will be a concentration of pollutants, C. And we are interested how much amount of pollutant is delivered into the system. And sometimes if there is a flow going out, outflow, we are interested in how much of those pollutants are leaving the system, because that's what is the exposure to the environment. So what mass balance suggests is that the total amount of pollutant in a system can be predicted based on what's coming in and what's leaving the systems. Because mass cannot be destroyed or generated, that means we can account for every other reaction. It can be converted from one form to another. So that's the whole point of mass balance. So that means total mass coming in has total minus total mass leaving the system. The difference is should be change in mass in the system, assuming there is no reactions. But if there is a reactions, that could be mass reacted. Notice that I say plus sign. Plus sign, when it's a plus sign, that means reaction create the mass from or transport the mass from one to another form. And if the reaction deplete the mass, then we can write negative term over here. So this is the very generic mass balance equations, which means that any change in mass in the system can be predicted based on the total mass coming in to the systems, total mass coming out of the systems, and any reaction. And this reaction could vary from system to system. So for example, as I said, we keep saying systems. So here is an example of systems. For instance, here on the left side, we have pond or a lake, and this is the boundary. We can suggest that, maybe this water is coming from groundwater. So this is in, and there is no outlet. And the only way things could leave the system is evaporations. So that's out. Or maybe there is a infiltrations. And so this is a lake or river. I'm sorry, lake or pond. Whereas the second one is more like a river or stream. In these systems, let's say we were interested in what's the pollutant over here. That's the system boundary. So that means we have to know how much coming in and how much leaving the system. If we know those two, we will be able to predict what is inside the system. And so this could be river, stream. The next one is a green infrastructure. For instance, here you can see this is an infiltration basin where most of the stormwater is coming in from outside, or there will be rainfall. So those are in, and there are outlet here. So based on those, we can calculate what's the concentration of pollutant that's leaving the systems after the treatment. So this is a green infrastructure. All right, so we know now how to identify systems, how to identify what's the inflow or outflow. So now next thing is to derive the equations. As I said, the generic mass balance equation is written here on the left side. That's essentially any change in mass in a system can be predicted based on the amount of mass coming into the systems. There is a typo here, and amount of mass leaving the system. plus anything is reacted or anything is produced by reactions or anything is destroyed by reactions. What we want is from this equation, we want to derive this final form in the generic equations, which is in concentrations. The reason is we measure concentration in the system. We can't measure mass. We only calculate mass based on concentrations and the volume. So that's why we can measure only concentrations. So that's why we are going to derive the equation in the form of concentrations from a mass equations. How do we do that? First thing, we know that concentration is basically mass over volume. So that means we can change mass to concentrations if we know the volume. So if we do write this one, rearrange it, it's mass equal to concentration time volume. Now dm over dt, which is derivative, would be d over dt cv. Because there are two terms, we have to take a derivative of each terms. That would be dv by dt plus, then we do v dc over dt. So what we did is it's a product formula for derivations. So now, because C and V are independent from each other, at least the C in these equations, then we could write that in this form. So let's see how to even, there are two conditions for that. First, in some system, concentration can be constant. That we can assume for, let's say, a river or a stream where source is constant. Think of like a wastewater treatment plants where it's discharging certain amount of pollutants and it's pretty steady. If the C is constant, then we can write this term dm over dt would be C dAV over dt, and the second term is b dc by dt. The derivative of a constant will be 0. But at the same time, if you think of volume, so this is case 1. The case 2, when volume is constant. And this is typically true if you are thinking of a pond or a lake. So think of a pond or lake. Typically, you can assume the total amount of volume is constant. If we do so, then we can see that dm over dt will take a different form. Again, from this equation, so the first term over here would be c dv by dt. We know the volume is constant, so derivative of that constant would be 0. So the first term is 0. The second term, which is v dc over dt, will be what will be remaining here. So this is how we can change the equation into different form. And this one we can write C, change in volume over time is flow rate. Flow rate is essentially how much volume we are adding into a system for unit time. So you can write C, Q. Q is equal to flow rate. And there is a third term here, which is a reaction term, dm over dt, reactions, would be, we can write the same way because it's reacting in a system with constant volume. We can write that this is a volume d by dt, volume time C reactions, concentrations, and usually reaction happens in a closed system, so that's what we account for. Then we can take the volume out, and this will be dc by dt reactions. And based on first order or second order reactions, we can always write dc over dt reactions for first order with kc. So this is a rate constant. And most of the systems are usually first order reactions, so we could assume this as a first order. But unless it's given a different order, then you have to solve different way. So now we have 3 different terms. We derived for very first term here, first term coming in, And then we can write this equation, these numbers, and we can write this to finally convert this to a systems. So now let's write this one. If we first term here, dm over dt, which is this mass of system, would be volume of a system times concentration of a system. So that means the volume is constant in a system, which is point. We can say that v dc over dt. That's the first term here. The second term here is mass coming in because of flow. So that means we know that the concentration is constant here, so that we can write C in, Q in. But if there are multiple sources, let's say there are multiple streams coming into the system, then we can account for that by adding a summation. This means any number of channels that come into the system. Same thing for the output. We can write C in, C out, Q out. Again, if you have multiple streams leaving the system, you can write as a summations. The last term, which is here, you can write plus V times dC over dt reactions. That would be Kc. Note that the dC over dt has a negative sign. That means we are assuming that the concentrations is going to decrease because of reactions. The reaction deplete the concentrations because some of the mass is reacting out. So that's the generic formula. So now anytime you have to write the mass balance generic formula, you would write this term. And this is again first order reactions. Order reactions. You will not write this one if it is not first order. Then you have to change that minus Kc to something else. For zero order reactions, dC over dt would be minus K. That's the zero order. And for second order reaction, dC over dt would be square. So essentially, any times the C to the power is the reaction order. So you can substitute the same value over here to change that equation for different order of reactions. So one of the specific case is steady state. Steady state means the concentration doesn't change over time in a system. And usually it's the case if the system is in equilibrium for input or output for a long period of time. So again, for the steady states, we can say that the very first term over here is 0 because concentration doesn't change over time. So again, steady state means dm over dt in a system doesn't change, means the derivative would be 0. That means we can say that mass of a system in a system would be always 0. And that means we can say that C times C system, V system would be 0. I'm sorry, this is not 0, this is constant. So same way we can write this is a constant. So this is a specific case. That means your mass balance equation, which is over here, will turn into only the right side. So that means you can write some C in, Q in. That's the total amount of mass coming into the system by different flows, minus the amount of mass leaving the system, that will be C out, Q out. Then the reaction term over here, that will be, I'll just write specific, I'll just change that DC reactions. You can write this one for first order, second order, or zero order reactions based on the type of reactions is equal to 0. So that's your steady state reactions, generic reactions for any mass balance equations. Again, here we are thinking 3 different terms. Number 1 is total mass coming into the system per unit time. This is mass leaving the system, mass out. And then this is mass reacted. That will be 0. That means there is no change in mass of the system over a period of time. So when I say mass, mass could be war or mass could be for contaminants. In this case, particularly over here, this is for contaminants. If you are looking for mass for war, there's no need to have a concentration term over here. This will be just Q. So that's all for the generic mass balance equations. Now let's get to specific case.